All right, so last time we looked at polynomials. We started looking at cubics, and we saw that cubics can cross the x-axis up to 3 times. We looked at 4th degree polynomials, and we saw they could cross up to 4 times. How many times do you think a 5th degree polynomial could cross? At most, it could be 5. And that would be a shape, if it did every turn that it could, and the axis was in just the right spot, 1, 2, 3, 4, 5. Okay. It could definitely be less than 5. It might not take that many turns. Okay. It all depends on the complexity of the graph. Okay, so 5th degree gets a little bit more complex with the turns. But what I want to focus on is really these spots right here. So those spots are what we call local extrema. There's 2 types of local extrema. There's local minimums and there's local maximums. When we use the word local, that means in that area. Right? So I'm not saying that this point is the lowest point the graph ever hits, because it goes down forever. I'm saying locally, it's the lowest point that it hits, meaning in the surrounding area, there is no other y value lower than that. In this area, there's no other y value higher than that. Okay, so those are called local minimums and maximums. So you could summarize local maximum and minimum with really the same definition if you want. The only difference is one word. A local maximum is a point on the graph that is higher than all other points around it. A local minimum is a point on the graph that is lower than all other points around it. And we find local maxes and minimums on the calculator. You can do it other ways, like with calculus, but we focus on doing it on the calculator. You can also find local minimums and maximums without calculus for certain shapes, like a parabola. In algebra, there's an equation for the vertex. So you could, if you know how to find the equation of a vertex in a parabola, that is technically a minimum. With a parabola, though, that's a special type of minimum. It's actually called a global minimum, because in a parabola, that is the lowest point, period. It's not just the lowest point in that area. There is nowhere that goes any lower than that, ever. Okay? So again, the term that you use to describe all local minimums and maximums is local extrema. So we're going to go over, again, real quick on the calculator, how you find a local min and a local max. And once you find it, how do you write your answer? All right, so let's try that. That question is asking you 2 things, so you got to be careful. It's asking you what the local minimum is, and then it's asking you where it is. The where it occurs, that's an x value. It means what number would you have to plug in for x to get the minimum. Okay, so the minimum itself is the y value. Where the minimum is the x value. Right, so let's try just typing that in. This one, you're not going to have to zoom way out. It's much, much easier this time than the homework question. I think zoom 6 is going to be perfect. All right, so first question. Does that graph have a local minimum?
Yes.
Yeah. A straight line wouldn't have a minimum. Okay? To have a minimum, you have to take a turn. And to have a maximum, you have to take another kind of turn. But yes, this has a minimum right there. So we're going to do second calc minimum. We're going to pick a point to the left, pick a point to the right, do our guess, and now we have to interpret the answer. So first of all, what is the local minimum? That's the y value. So how low do the y values go in that area?
Negative 3.1.
Yeah, we'll go to 2 decimals, so negative 3.08. But yeah. So the local min is negative 3.08. This occurs when, so this occurs when x is about 1.15. So any question on the difference between what the minimum is versus the number you plug in for x to get that minimum? Yeah?
Do we have to write the answer exactly like that?
As long as you express that idea, that's fine.
Okay.
Because they are asking, if you write like a coordinate, I wouldn't give you full credit for a coordinate, because then I don't know if you know which number is which.
So we just look for the minimum of the second kind of like dip in the line.
Yeah, in that case, that's where it happens to be. Some graphs, could be more complicated, and you could have several minimums. And it might say find them all. So then you'd have to find each minimum. And remember, what the minimum is the y value. Where it occurs is the x. Yep. Now, it would be the same idea for the maximum. Does anyone have a question on how you would do maximum on the calculator?
Is it just the second calc and then maximum?
Yeah, it's just second calc and then maximum. This graph happens to be symmetrical, so you get kind of the same answer. Just the positives and negatives kind of switch. So the maximum is 3.08. So I'm going to write this answer a little different. The max is 3.08, and this occurs when x is negative 1.15. So at least if you write it that way, I know you know the difference between what the maximum is versus where it occurs. Okay, and what finding mins and maxes does is allow us to explain where a function is increasing versus decreasing. Okay, so look at something like that. If you find this point and this point, you can break that function up into 3 sections. This I would consider to be a section that is increasing. This is a section that's decreasing. And that is a section that's increasing. So that's what we're going to describe now, increasing versus decreasing. So let's look at this one. And I didn't actually find numbers. Okay, these are just letters, A, B, C, and D. Can somebody give me an interval where the function is increasing from what to what? Yeah. B to C. And we usually use an open interval to describe this because right at the B, it's not increasing or decreasing. It's flat. Think like if you poured water in there. At B, the water would be perfectly flat. Right? And same with C. If you were standing on the top of the hill at C, it wouldn't feel like you're going up or down. It's flat. How about where is that function decreasing? Yep.
Between A and B.
Yep, it's decreasing between A and B.
And C and D.
and between C and D. So notice what happens as you go from increasing to decreasing. Anytime you have a graph that goes from increasing to decreasing, you're going to get a local what? Yeah?
What does a local max look like on a parallel?
Just be the top of that.
Oh, the top.
Yeah. Yeah.
Local extrema?
What's that?
Extrema?
Local extrema are all the mins and maxes. Yeah. So what happens when you go from increasing to decreasing, like point C? What do you always get in a graph? Yeah. You always get a local max. Anytime you go from any kind of increasing to decreasing, you get a local max. How about if you go from decreasing to increasing?
Local min.
You get a local min. Yep, exactly. So let's go back to the problem we just did and see if we can describe where our function is increasing and where it's decreasing. But this time I don't want to use A, B, C, and D. I want to use the numbers. Okay. So I'm going to just make this example 4. So describe the increasing and decreasing intervals. And to describe an interval, you always use the x value. Okay. All right. So let's start with, let me make this a little bit bigger. Okay. Let's start with this one. So looking at that graph, what's happening in this? We'll call this section 1, we'll call this section 2, and we'll call that part section 3. And there's my local extrema. What's happening in section 1?
Increasing.
The graph is increasing. Okay. The graph is increasing. Let's start. How low does section, or let's say it this way, how far to the left does section 1 go?
-2.
So that means that section 1 would stop right there if it only went to -2.
Oh. -3.
So that would mean that it stops right there. So how far left does it go? Yep. Negative infinity. That section just keeps going to the left forever. Okay, so from negative infinity up to, what's the highest x value you could plug in and still be in section 1?
The highest what value?
The highest x value. What is it?
-1.15.
Yep. That's the highest x value you can plug in and we'd still be in section 1. So any number that you plug in from negative infinity up to that x value right there will put you on section 1, which is increasing. And there's another interval where it's increasing too. What section is that?
It's,
Section 3.
Section 3. What's the lowest x value you could plug in and be in section 3? Yeah?
-3.08.
So negative 3.08 would mean you could plug in a number like over here. That would put you in section 1.
0.
0 would put you in section 2. 1.15. That's the lowest x value you can plug in and still stay to the right of that dotted line. Okay. So 1.15. And what's the highest x value you could plug in and make sure you're to the right of that dotted line? Yep, infinity. So those are the two intervals where this graph is increasing. Now I want to write down where it's decreasing. So what x values could you plug in so that you are now between the two dotted lines? You have to stay in section 2. From what to what? Yep.
For the increasing part, I think you swapped the signs on 1.15.
So from negative infinity up to negative 1.15, that's right there. And then
Oh, it's
from
on the X.
1.15 to infinity. So yeah, that's okay. Yep.
For decreasing between negative 1.15 and positive 1.15.
Yep. So if you plug in a number between negative 1.15 and positive 1.15, you will be between those two solid lines, and that will put you in section 2, which is decreasing. So to figure out where something is increasing and decreasing, the first step is to find all the local minimums and maximums. Now, if you have something that's a straight line, well, that's increasing forever. It never starts to decrease because lines can't take a turn. Okay? So for something to go from increasing to decreasing, it has to turn. And only things with exponents of 2 or higher can turn. Linears cannot turn. Yep.
Can I ask how to use or, not and?
Because you can't be in both intervals at the same time. You could either be on this interval or in that interval. But you can't be in this one and this one at the same time. That's how I've always written it. I wouldn't be really too picky about that in this case. I think you could really write it either way. It won't be something that is important for you to know for the test though, like that. I'm sure mathematically, maybe there is a one right way, maybe I've been doing it wrong all these years. But as long as you know the both intervals and how to find them, you're okay. Okay. Any questions on that? Yeah.
What would happen if you stand right at 1.15? Would it be decreasing or increasing?
It would just be like flat.
All right.
Yeah, right at 1.15, it's like the top of the hill. It's like it's not up or down, so it doesn't count as either. That's why I don't use any brackets on my intervals. Yep. Okay. All right, so last thing we're going to look at has 3 different topics. They're all pretty simple. And the first 2 are connected to each other, continuity and intermediate value. Continuity actually ties in with the question that somebody just came over and asked me a minute ago about functions. So I'm going to start with talking about what continuity means. So when we draw something on the calculator, it is possible that you can draw it in one section without ever lifting your pencil. And sometimes the graph is in 2 separate sections, and you do need to lift your pencil. When you type in something that has a fraction, make sure you use parentheses around the denominator, just like I did there. Okay, let's graph that. Now, is there a number that I'm not allowed to use for x there? Yeah?
3.
Right, we can't use 3, so something weird is going to happen when we get close to 3 on the x-axis, because you're not allowed to use 3. So look at what happens. Is that a graph that I could draw without ever lifting my pencil? Or would I have to draw one piece, lift the pencil, and draw the second piece? Yeah, I'd have to lift the pencil and draw it. Yep. Okay, how about this graph? This is called an integer function. I think we looked at it before. It looks like a set of steps. Could I draw that without ever lifting my pencil? No. Now, I have to lift my pencil here, but it's not because I divided by 0. It's because the integer function rounds your answer to the nearest integer. So you don't get decimals in the y values ever. You can get a 2 in the y value, you can get a 3 in the y value, but you can't get anything in between because of rounding. Okay? Not because of dividing by 0. So that's a little different than the first one. But I still have to lift my pencil when I draw it, which is the point. Okay, now look at this one. X squared minus 2x plus 4. When I draw this one, do I have to lift my pencil to draw that shape? No, that one's different. So we're going to talk about what does that mean then? How would we describe the first two compared to the last two? Or the first two versus the last one? Well, the last one that I drew was continuous because I never had to lift my pencil to draw it. So a function is continuous over an interval. Sometimes we name an interval, like if you had a parabola and we said you started here and you stopped here, so you're looking at that little section, you could name that section something. You could name it section J. Sometimes, I think in the last problem I did with you guys where it was increasing and decreasing, I named the sections with numbers, 1, 2, and 3. Okay, but if you have a section, call it whatever you want, that starts at a number and stops at a different number, A, B, and you never have to lift your pencil while you're tracing from where you started to where you stopped, then that is called continuous. I'm not saying the whole graph is continuous. This one is. But I'm just saying, at least from where I started to where I stopped, I never had to lift my pencil in that section. Does anybody have an idea what the opposite of continuous is? Like if you try tracing from a starting point to a stopping point and you have to lift your pencil to do that.
Non-continuous?
Non-continuous is a good guess. They call it discontinuous. Yeah. But discontinuous means that it is not continuous. Okay, so here's something that's not continuous. Here's A, here's B. I want you to trace along that graph from A to B. Well, trace along A, you go down forever, then you have to lift your pencil, put it back down, and now you can trace to B. I had to lift my pencil to do that. That is discontinuous. Same thing with the steps. That's A and that's B. I cannot trace from A to B without lifting my pencil, putting it back down. That is another example of discontinuous. So any question on what it means to be continuous versus discontinuous? Okay. So let's draw that picture. And I want to describe two intervals that are continuous and two that are discontinuous. First of all, what number would be a problem if you tried to fill it in? 0. And that's where the discontinuity is. The point of discontinuity in this graph is when x is 0. So any interval that tries to trace through the number 0 is going to be a problem. So let's look at our graph. Calculator doesn't do a great job with it because it starts to get a little too steep. But this part really should just keep going up and get closer. And this should keep going down, getting closer. There's asymptotes in this graph. Okay, we're going to talk more about those in chapter 4. But that's what it should look like. So let's start with continuous. Can somebody give me a number that I could start at on the x-axis, a number that I could stop at on the x-axis, and I never lift my pencil to trace between those two numbers? Yeah?
2 and 5.
So from 2 to 1, 2, 3, 4, 5, yes. That section in black is a continuous section. Do you want to include the 2 and the 5 or not include them? Include it. It doesn't really matter. You could include them, not include them, but you can trace between 2 and 5 without a problem. What's another section that I could trace between that would be continuous? Yeah?
-2 and -5.
Negative, just make sure you put the low value first, high value second. But yeah, -1, 2, 3, 4, -5 to -2, traces from there to there. Perfect. Now let's write a section that's discontinuous. What would be a number that I would start at and stop at that I could not trace without lifting my pencil? Yep.
-2 and 2.
-2 to what?
2.
Yeah, you can't go from -2 to 2 because there's the first part, and then eventually you come back in up there. All right, anything that passes through the point of discontinuity, which in this problem is 0. It's not always 0, but in this one it's 0. Okay, so another one would be -8 to 13. I can't go from a negative to a positive in this graph without lifting my pencil. Okay. Any question on that? Okay. So there are really 3 different ways that a graph can have a point of discontinuity. One of them is if you have a function that would cause you to divide by 0. Wherever you would divide by 0, that's a discontinuity. And that's because the graph is undefined at that value. When you try to plug in 0, 1 divided by 0 is undefined. Can't do that. Another way that you can have a discontinuity in a graph is with like the integer function. That's a different kind of discontinuity than the first one. With the integer function, you are never dividing by 0. That doesn't happen. It can't happen. What does happen is the integer function itself rounds the answer without any decimals. That's how it works. So if you round without any decimals, you could get an answer of 2. You could get an answer of 3, but you'd never get like 2.6. That's impossible. So there's a jump in the range. And that's because of the behavior of how rounding works when you round to the nearest integer. Both of these are very noticeable. Okay? When you try to divide by 0, you get a graph that has 2, sometimes it's more, but a lot of times it's like these 2 curved pieces. Very easy to see. Okay. When you do the integer function, you get a series of steps. Very easy to see that you're lifting your pencil up and putting it back down. This last one is not easy to see. You can't see it on the graph. Okay. Let's type this in and see what happens. So we've got x squared plus 3x plus 2. And I'm going to divide by x plus 2. Okay. Now, Is there a number I am not allowed to plug in for x?
Negative two.
Cannot plug in -2. Let's watch the graph and see what happens as you get close to -2. So watch -2. Looks like we just passed right through it without any problem at all. There's nothing in this picture that indicates something weird is happening at -2. -2 is right there. There is something happening, because if I go to the table and I type in -2, I get an error. I can't plug -2 in. So what's happening here is what's called a hole. When you have a hole in a graph, you can't see that it's there. Okay? The only way to see that you have a hole is to go back to the original problem. Let's factor the numerator and watch what happens. How would the numerator factor? Yeah? +2 plus 1. What do you notice now that we factored it?
That's how to put x plus 2's.
Yeah, it's almost like these x plus 2's cancel out. And the picture that you get when you type in what's in black essentially is going to look like this. Almost. They look almost identical. The difference is the one in black has a hole right there. So if we were going to sketch that one in black by hand, this is how you would sketch it. You exaggerate it and you show that the graph has a hole, like that. So the only way that you know a graph has a hole is to factor it. And if you get a common factor in the top and in the bottom, that means this would be a hole in the graph. Okay, so that's the trickiest one to tell. That you have that is a spot where you'd have to pick your pencil up, put it back down on the other side of the hole, and then keep going. Now, that hole is infinitely small. Right? You can go to your table, you can type in -1.99. That's not -2, so that one works fine. You can type in -2.01. It's close to -2, but it's not -2. So it works fine. It's just -2 that doesn't work. Now, if I take the numerator and I change it so it's x squared plus 3x plus 2.1, does that still factor as x plus 2, x plus 1? No. I just messed up the factoring in the top. So now it won't factor into x plus 2, x plus 1, and you're going to see it doesn't have a hole anymore. So just by changing that number a little bit, now it's got those two curved pieces that look very different. Okay. So it has to be a very, very precise situation to have a hole. It has to factor in the top and have one of the factors in the bottom as well. Okay, so any question on those three different kinds of discontinuities? This one is really the same as the first one. It's an undefined value at -2 because you're trying to divide by 0. You just can't see it in a picture. But it's really the same thing. All right, so we talked about the domain of polynomials, and that kind of leads us to this statement. The domain was all real numbers. Well, whenever you draw a polynomial, whether it's a parabola, maybe a cubic, you never have to lift your pencil anywhere that you draw a polynomial. That means that every polynomial is continuous all of the time. You can't find a section in a polynomial that is discontinuous. If you draw something and it has a section that's discontinuous, then I don't know what you drew, but it's not a polynomial. Polynomials never have to lift your pencil to draw them. And if something is continuous absolutely everywhere, not just a small section is continuous, I mean, all of it is continuous. That's called a continuous function. So polynomials are continuous functions because you never have to lift your pencil to draw them, ever. That's the definition of a continuous function. Polynomials are the only category of functions that, or they're the most common category of functions that are continuous. Some trig functions are continuous when we start to study trig, like sine waves and cosine waves. Those aren't polynomials, but you never have to lift your pencil to draw them. So there are other functions that are continuous besides polynomials, but this is a pretty big group of them. Question on that idea? All right. So let's say that I had something like this. And down here, I'm just going to make up a coordinate for that. 3, 2. That's the coordinate 3, 2. This is the coordinate 20, comma 32. Way up there. What y value am I starting at in that picture? Yeah, what y value?
2.
Yeah, I'm starting at a y value of 2. And what y value am I stopping at?
32.
32. So I'm going from 2 all the way to 32. Now, did I ever lift my pencil as I went from 2 to 32? I might have gone back down, like I didn't go straight to 32 like a line, but eventually I curved and around and I got there, right? I got to 32. So at some point, did I pass through the number 5 on the y-axis? Yeah, why would I have to pass through the number 5 going from here to here without ever lifting my pencil? Because it's continuous, exactly. Right? If you have a continuous function and you start at a number and you stop at a number, I guarantee you'll go through every value in between 2 and 32. You have to. There's no way to get from 2 to 32 if you never lift your pencil without going through every number in between. Okay? It's kind of like if you had a pot of water at room temperature and you start to heat it up. Let's say you heat it from 70 degrees to 100 degrees. It's going to go through every temperature between 70 and 100. 71, 71.9, 72.6. It has to. It can't skip temperatures because heating water is continuous. And that idea that you hit every single value between two numbers, that's called the intermediate value property. And that's all I'm really going to say about that. And then we're just going to do the last thing. So, intermediate value property basically means if you have a coordinate, this time I'm not going to use numbers, I'm going to use x and y. And you're starting at this y value, and you are stopping at that y value. I guarantee you, you will go through every y value between this one and this one. But that only applies because you never lifted your pencil when you drew it. If you lift your pencil, then no. Okay. If you had something like this, and you had a y value here and a y value here, no, you do not go through every y value between the low one and the high one because you lifted your pencil as you do it. So you skipped. Right? So the intermediate value property only applies to a section that you've drawn without lifting your pencil and guarantees you'll go through every y value in that section between the start and the stop. Now, you might go through more than that. You might go through and do this. So you went even lower than where you started. Well, the intermediate value theorem doesn't guarantee that. It doesn't guarantee you're going to go lower. You could, but it just guarantees that you're going to go through every y value between that line and that line right there. You'll hit every y value in that section. Any question on that? Okay. So that's all I wanted you to understand for intermediate value theorem. Okay. So the last one is easier than continuity and intermediate value. It's much more concrete. It's not really abstract at all. End behavior describes what happens on the very left and right edge of a function. So let's say you had a cubic that looked like this. If I wanted to describe the end behavior of that function, that means to describe what's happening here and what's happening here. On the left side, it's going down. On the right side, it's going up. That's called the end behavior. If I had a parabola, what would you say is happening on the left side of it? It's increasing. It's going up. What would you say is happening on the right side? It's also increasing. It's going up. So there's really 4 different types of end behavior you can have. You can have an up and an up. You could have a down and a down. Or a down, up, down. Those are the only 4 things that can happen with polynomials. So I want to look at how do we write that? Like how do you write up, up? Or how do you write down, up? Well, there's 2 ways we can write it. I'm not going to graph x cubed on the calculator because it looks just like what I have on that black graph on the right. So if you graph x cubed, I'll just draw it a little bit better. It's going to look kind of like that. It doesn't have as much of a turn in the middle. It has like a little bit, but it never really does as much of a turn. So the way that you would describe this graph is you would say that the behavior is down on the left and it is up on the right. That's one way to describe it with arrows. Now the other way to describe it is more in words, okay, rather than drawing this picture. When you describe it in words, you have to write 2 things. You have to describe it on the right side and on the left side separate. This is going to be described by this. And that is going to be described by that. So let me read to you how to pronounce that exactly the way it's written. And then let me say it in a way that's going to be easier to understand. So this red box says the limit of f of x as x approaches infinity is, and then you write an answer. A simpler way to say it, what is happening to the y value as x heads to the right? Infinity is to the right. Okay. So what's happening to the y value as x heads to the right? So look at this graph. As you continue to head right,
It increases.
it increases, and what does it increase towards?
Infinity.
Infinity. That red box is how you describe the arrow with the red box. Okay, now the green box, the limit of f of x as x approaches negative infinity. F of x is just another name for y. What's happening to y as x heads to the left? Okay, so look at the graph. As x heads to the left, what's happening to the y value?
It's decreasing.
It's decreasing. And what is it decreasing towards?
Negative infinity.
Yep. So either notation is fine. I will tell you the limit notation is a lot more formal. Arrow notation is, I mean, it's easier for some people to understand at first, but it's not really used that much. Okay, so any question on that? So those are the, actually I think I have that chart, yeah. Well, I'll show it to you here first. So those are the 4 different types of end behavior. Both up, both down, and then one of each. So if you want a picture to go with each one, think of a parabola flipped. Think of like something like that. And something like that. Even if it takes more twists and turns in the middle, like if it does this, I would still say that the end behavior of this one is up on the left, down on the right. I don't care what it does in the middle. I can ignore all of that. Up on the left, down on the right. So let's graph x to the 4th and just see if you can tell me what the end behavior is. X raised to the 4th. And you could just watch me graph it. How would you describe that end behavior? We can use the arrows, that's okay.
It's both going up.
Both going up. Yep. So this end behavior is up, up. And now let's do it with a negative in front. Okay, we learned a couple weeks ago, negative causes a reflection. So the end behavior now is down, down. Yep. Any question on that? So how can we quickly tell that it's up, up, or down, down? What if we don't want to graph it? There is a way that you can quickly tell what the end behavior is going to be. So if you have a really, really long polynomial, okay, something like that, most of those terms there, they don't matter at all. The only one that matters is the leading term. That's the only one that's going to control the end behavior. So that is my leading term. It's the one with the highest, actually I wrote it over there, so I won't write it again. It's the term with the highest exponent. Because that term has the highest exponent, that term is going to completely control what the end behavior looks like. Does it control all the little twists and turns in the middle? No. But it does control what the end behavior is going to look like. And there's only 2 things you need to look at to find the end behavior. 1 is that exponent, and 2 is that number in front. If the exponent is even and the number in front is bigger than 0, you're going to have up, up. So that would be something like 3x squared. If the exponent is even and the number in front is a negative, that would be like a down, down. If the exponent is odd and you have a number in the front that is less than 0, when you graph that, it's going to go up on the left, down on the right. So this chart summarizes what the end behavior is going to be. And this term has a name. Besides the leading term, this term is called the end behavior model, which you might see me abbreviate EBM. So the term that controls the behavior of the polynomial is called the end behavior model. It's always the term with the highest exponent. So let me just make one up. Anybody think they can tell me what the end behavior model would be in that polynomial? Again, it's the leading term. This term, oops, is called end behavior model. Yep.
4x cubed.
Exactly. So what that means is if you graph this in y1 and you graph that in y2 and you zoom out enough, they're going to look almost exactly the same. This one might take some little twists and turns in the middle, but overall, that is going to describe what it looks like, and that's called the EBM. So it's a very easy thing to find. It's just the term with the biggest exponent. And that's everything that we were going to do in 3. Okay, so I'm not going to have time to put a list of topics on the board now, but I'll do that while you're at lunch. And then if you want to check the video, the topics will be in there. If somebody comes for extra help, I might make a video as well. We'll see if people come for extra help. Okay, so let me change a couple things. And on page 161, definitely changing a few questions. Those are fine. So, number 9, 12. Okay, 21 to 22, that's looking at some pictures. 23 says find the end behavior type. Just to be clear, when they ask about end behavior type, that's where you draw arrows. Okay, you tell me the direction. If they ask for the end behavior model, that's where you give me a formula like that. So the type is the arrows, the model is the formula. 21 to 25, and the rest of that's fine. Okay, so I'll make this a little neater for you. So 21 to 25, 9,231. Okay, and as I said, I'll put the list of test topics on the board in just a little while.